Hello, welcome. My name is Theo, and I'll be guiding you through why the samples behave the way they do, why some are solids like silver, and while others are gases like fluorine. Um, I'm hoping these slides help you better understand my analysis report and how to identify atoms accurately. Uh, Before we look into bonding, I'll review some fundamental concepts. First, atoms, they always seek stability. They want to achieve a balanced state, which usually means having a full outer shell of electrons. And in other words, that's a stable electron configuration. The key to determining how atoms achieve this stability is electronegativity, which essentially is how strongly an atom pulls electrons towards itself. Um, we measure this on a scale that typically ranges from 0.7 to 4. Atoms like fluorine have a very strong electronegative pull at around 4, while atoms like sodium and silver, which are both metals, are more willing to let electrons go because of their low electronegativity, which is around 0.7 to 1. Electronegativity determines how atoms bond. When there's a big difference in electronegativity between atoms, one atom transfers electrons to another, and when more evenly matched, they share instead. Next slide. So let's look at the four main bonding types, starting with metallic bonding. Metallic bonding happens between metal atoms like silver and barium, our samples. These atoms have low electronegativity, meaning they don't hold on to their electrons. They don't hold on to their electrons very tightly. So what happens instead? Their outer shell of electrons break free and form what is called a sea of delocalized electrons that flow around the positive metal ions. This is why metals conduct electricity so well. The electrons can move more freely through the material. It's also why metals are so malleable, and you can bend and shape them without them breaking. Next, we have ionic bonding. This comes when you have a metal with low electronegativity meeting a non-metal with high electronegativity, like sodium and chlorine in table salt. The sodium atom donates an electron to the chlorine atom. This turns sodium into a positive ion and chlorine into a negative ion. Opposite charges attract, so these ions pack together in a regular pattern called a lattice. This creates a very strong attraction in all directions, which is why ionic compounds like salt have high melting points and are usually solids at room temperature. Next are the covalent bonds. These are how non-metals bond together, and since non-metals generally have high electronegativity, neither atom wants to give up their electrons completely. Instead, they share. There are two types of covalent bonds. Simple covalent, like fluorine atoms, share a pair of electrons to make the diatomic fluorine molecule F2, and giant covalent, like diamond, where carbon atoms link up in a massive network. And the difference between these two is pretty big. Fluorine is a gas, and diamond is one of the hardest substances known to man. The takeaway here is that the electronegativity difference is your first clue about what type of bonding is occurring. A small difference is probably covalent, and a big difference is likely ionic. Okay, next slide. So how does bonding translate to actual properties we see? First, metallic bonding gives us solids like silver that conduct electricity and heat well, and are also malleable. Ionic bonds are also solids at room temperature, but for different reasons. The strong electrostatic forces in the ionic lattice mean you need a lot of energy to break it apart. And that's why table salt doesn't melt until it reaches 801 degrees Celsius. Alternatively, with simple covalent molecules like fluorine, the bonds are strong, but between the molecules they have weak attractions, so at room temperature these weak forces can't hold the molecules together in a solid, and instead they move around as gas. To turn fluorine into liquid, you need to cool it down to around minus 188 degrees Celsius. Giant covalent bonds are the opposite to this. Since every atom is in a massive network, like diamond, for example, they are incredibly rigid and have extremely high melting points. Diamond doesn't melt until it's around 4,000 degrees Celsius. Next thing we're looking at is shape. Shape isn't just what atoms are connected, but how they are arranged. Electron pair repulsion theory is our guide here, EPRT, which tells us electron pairs, whether they're in bonds or as lone pairs, repel each other. Lone pairs, which are electrons that aren't shared in a bond, take up more space and repel more strongly than bonding pairs. This affects the final shape. For example, methane has carbon at the center with 4 hydrogen atoms. Carbon shares 4 pairs of electrons with these hydrogen atoms, no lone pairs. To maximize the distance, the bonds point to the corners of a tetrahedron with angles of 109.5 degrees, which is also a common shape in bonds. Alternatively, we have ammonia. Nitrogen has 5 outer electrons. These are used in bonds with hydrogen, having 1 lone pair. We now have 3 bonding pairs and 1 lone pair. The lone pair then pushes the bonding pairs close together, pushing the angle down to around 107 degrees, and this gives the bond a pyramid shape. The ammonium ion shows how adding a hydrogen changes things. The nitrogen now has no lone pairs. All 4 pairs are used in bonds, making it tetrahedral again with a 109.5 degree angle. So why does shape matter? It affects how molecules interact, how they pack together, and ultimately their physical properties. Next slide, slide 6. So let's discuss what holds molecules together when they aren't bonding. These are called intermolecular forces, and they come in 3 main types. First, there is the van der Waals forces, which are the weakest out of the 3. These occur in all molecules. They're caused by temporary uneven distributions of electrons. At any moment, one part of the molecule might be slightly more negative than another. These fleeting dipoles induce similar dipoles in neighboring molecules, creating weak attractions. The bigger the molecule, the stronger these forces generally are. Next, there are permanent dipole-dipole forces. These occur in polar molecules, molecules where there is a permanent uneven distribution of electrons because of differences in electronegativity. A good example is hydrochloric acid. The chlorine pulls electrons more strongly than the hydrogen, creating permanent positive and negative ends that attract electrons. Strongest of the 3 are hydrogen bonds, which are special cases of dipole-dipole attraction, but are much stronger. They occur when hydrogen is bonded to fluorine, oxygen, or nitrogen, 3 very electronegative elements. The hydrogen becomes so positively charged that it can strongly attract lone pairs in nearby molecules. For example, in water, hydrogen bonds explain why the water has such small molecules, why ice floats, and why it has such high surface tension. So let's apply everything we've learned to the samples. First, fluorine gas is a simple covalent molecule with weak van der Waals forces between molecules, and that's why it's a gas at room temperature. The molecules don't stick together well enough for it to form as a liquid or a solid. Then there's krypton, which is even more simple as it's a noble gas, meaning its atoms don't form molecules at all. Single krypton atoms have very weak van der Waals attraction. And then there's silver and barium, which are both metals with metallic bonding. Their delocalized electrons create strong attractions throughout the entire structure. and that's why they're solids at room temperature and are malleable. Remember this chain of reasoning. Start with the element, then consider their electronegative differences, then predict the bonding type, and then from the bonding predict the structure. From the structure predict the intermolecular forces, and finally predict their properties. And this is how we can understand and identify samples. Okay. So we're on the last slide now, and here are our key takeaways. Electronegativity is the starting point for predicting how atoms will bond. Large differences means ionic, small differences means covalent, and metal with metal means metallic. The type of bonding directly determines physical properties. Continuous strong bonding throughout a structure means solids with high melting points, and weak forces between separate molecules means gases or liquids at room temperature. Molecular shape matters, and we can predict it using EPRT, electron pair repulsion theory, by counting bonding pairs and lone pairs. And then we have intermolecular forces like van der Waals, dipole-dipole, and hydrogen bonds. They all explain the difference between substances that might seem similar but behave differently. Thank you for listening and watching. I hope this gives you a better understanding of atoms, bonds, and their structure, and